So hello everyone. Let's start with the numerical analysis and design lab assignment 3 solutions. So hello, my name is Siddharth Gupta and my roll number is IT22482. My enrollment number is GE2402066. So let's start. The first question says to find the roots of this equation using bisection method. So the target equation is this. The first, what we would like to do, first we will take two values and we will find the values at that function. It is the guess values. We will take two guess values and we will find the value of the function at these values. So the value of the function is coming -1 and 1 as fa into fb is negative in this case. So we could say that the root will lie between these two guessed points. So now moving on to the first iteration, the midpoint for bisection is a plus b by 2. So here midpoint is coming 1.5. We will find the value of the function at 1.5. If the value is coming negative, we will put this value of x1 into a. If the value of fx comes positive, we will put that value of fx into b. We have already seen it in the algorithm of bisection method. In next case, we will do the same. In next case, we will do the same. We will do this till 13th or 14th iteration. And you could see that at the 13th or 14th iteration, the root will converge somewhere to x is equal to 1.6806. Okay. So how you will check that when we need to solve fx? So when your fx will come somewhere around 0.0001, at that time you need to stop your iteration and the value of x at that case will be the root. So here we have solved the first equation using bisection method. Now we need to solve the same equation using Regula-Falsi method. So for Regula-Falsi method, you already know. Uh, Again, we will do the same thing. For a is equal to 1, f1 is this. For b is equal to 2, f2 is this. So what we will do now, again the same thing, as f into fb is negative, so the root will lie between this to this. The formula is x is equal to a into fb minus b into fa upon fb minus fa. Now we will substitute these values for first iteration and we will find the value of x1. Again we will do the same thing. If f of x1 is coming negative, we will substitute the value of a x1 into a, otherwise we'll substitute the value of b into x1. So again we will do the same thing, and for iteration 1 or in iteration 7 or 8, it will converge and it will come somewhere around x is equal to 1.61803. So this is the Regula-Falsi method for this equation, and the root is coming same as it came in bisection method, but it will take lesser number of iterations. Now coming to the secant method, for the secant method you already know the formula is given below. F of xn plus 1 is equal to xn minus f of xn into xn minus 1 upon f of xn minus f of xn minus 1. Initially, we will take the same values, x is equal to 1, x is equal to 2. For f of 1 is negative, -1, f of 2 is positive, f into f is negative, the root will lie between x of 1 and 1 to 2. Again, we will do the same thing, put the values in the formula, and again, it will be the same thing. If f of x is less than 0, to transfer the value of a into x1, or transfer the value of b into x1 if it is positive. Again, we'll do the same thing, and in the third or fourth iteration, it will converge and the answer will come somewhere around 1.618. That answer will already come. So this was the secant method. Now we need to solve the same question using Newton's-Raphson method. For Newton-Raphson method, you already know the formula is xn plus 1 is equal to xn minus f of xn upon f dash of xn. Now, what we will do, first we will calculate the derivative of this equation. The derivative of the equation is 2x minus 1. So, again we will take an initial guess. Let's say x is 0 is equal to 2. We will find the value of the function and its derivative at x is equal to 2. The first iteration will be xn is 2 minus f of xn. F of xn we already find it 1 and f dash of xn we already find it 3. So, the first iteration is this. Similarly, we will find the second iteration, third iteration. So, look here. If we will find the second iteration, third iteration. If and again we will substitute, like x2 will be the new x3, x4 will be the new x3, and we will stop until the answer will come, the function will come somewhere around 0.001. We will stop there, and the value of x3 will be the root. So here, and in Newton-Raphson you can see it has been converged in only 2 to 3 iterations. It is more faster than all of the previous methods we have known. So Newton-Raphson is faster and it will be converged in the third iteration only, and the answer will come 1.61804, the same answer as we have seen in the previous three methods. Now coming to the last 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 method for solving the roots of polynomial. That is the 6 point iteration method. For 6 point iteration method, we will represent this equation in the form of x is equal to gx. So we can we can take this x and 1 in the right hand side. So x square will be equal to x plus 1. Now we can say that x is equal to under root x plus 1. So what we could do, now we can see that we have represented this in the form of x is equal to gx. So gx has come under root x plus 1. Now we will check that the mod of gx is less than 1 or not. So we took a point and we checked that yes, it is less than 1. So the iteration will converge. Now what we will do, it is our iterative formula which has been made from here. This is the iterative formula which we have formed. Now what we will do, just we will take a guess and we will put these values. So first what we did, we put the value of x0 is equal to 1.5 here. So the answer comes for around 1, x1 comes around 1.58, 1.6. Now what we will do, this x1 will be put it as in the x2. Then this x2 will be put in x3. This x3 will be put in x4. This x4 will be put in x5. And finally, in 3 to 5 equations and 3 to 5 iterations, it will converge and the answer will come somewhere around again 1.6180. So this is the first question where we have solved the golden equation x1 minus x minus 1 using five method, that is bisection, Regula-Falsi, secant, Newton-Raphson, and fixed point iteration method. Now we will coming to the second question where we have been given some data points and it has been said to evaluate f of 9. Now we can already see that the data points are not equidistant. So we will use either Lagrange's interpolation or divided difference interpolation. So for Lagrange's interpolation, the formula is given here. Now what we will do, first we will find the and first term, or you can say the term 0. So for term 0, x0 is equal to 5 and y0 is equal to 150. You can clearly see x0 is equal to 5 and y0 is equal to 150. So we will put the value in the Lagrange equation and the first term will come somewhere around minus 1 by 9. Then we will multiply it with y0, that is 150. So answer will come minus 16.667. Similarly, we will find term 1, term 2, term 3, term 4, and we will add all the values. We will add all the values and we will get the answer somewhere around. Also don't for also note that we are finding the value at x is equal to 9. We are finding the value at x is equal to 9. Here also put the value 9, put the value 9, put the value 9, put the value 9, and finally you can see the answer will come somewhere around 810. So this is the first part of the question where we have solved this this data points using we have founded f of 9 using Lagrange. Now we could say that for Hermite we need both fx1, fxi, and f dash of xi. So here both are not given. So we cannot use Hermite interpolation. Also we cannot use forward or backward as I already told you that the points are not equidistant. So what we could do, we could use either Lagrange's or divided difference. Lagrange's I have already explained. Now we are coming to divided difference. For divided difference, what we will create a divided difference table, that is f of x0 comma x1 will be equal to f of x1 minus x0 upon x1 minus x0. F of x1 minus x2 will be equal to f of x2 minus f of x1 upon x2 minus x1. F of x2 comma x3 will be f of x3 comma minus x2 upon x3 minus x2. F of x3 comma x4 will be x4 minus f of x4 minus x3 upon x4 minus x3. So here we will calculate the first divided difference like this, and again we will calculate the second divided difference, the third divided difference, and the fourth divided difference, and then we will put all these values in the Newton divided difference formula. The Newton divided difference formula states that fx is equal to y0 plus x minus x0 delta 1 plus x minus x0 x minus x1 delta 2 plus x minus x0 x minus x delta 3. What we will do, we will substitute all these values and we will find the evaluate the function at x is equal to 9. So we will see that value will come same as Lagrange, that is 810. So here we have concluded the second question where we have been finding the function value at 9 with both divided difference and Lagrange interpolation. Now coming to the third part where it is numerical differentiation. For numerical differentiation, nothing new. Just from Lagrange or divided difference, first you find the equation, don't put the value 9. Find the equation, find its derivative, and then put x is equal to 9 and you will get the answer. So it is very easy. First find the equation, differentiate it, and then put x is equal to 9. So it is very easy. Find the equation using divided difference or interpolation, Lagrange interpolation. Put the value x is equal to differentiate and put the value x is equal to 9. So here we have solved question number 3. There are one more part in this question about finite difference. So here again the same thing. We cannot, there is unequal x spacing, there is non-equidistant point, so we cannot apply numerical differentiation also. So we have concluded the third question. Now coming to the fourth question, that is we need to derive Simpson's trapezoidal, and these all using using numerical quadrature, or you can say using or you can say using general quadrature formula. So what we will do, uh, for integral a to b f x dx, we will replace the function with Newton's forward difference polynomial, or you can say we will take x is equal to x0 plus UH and dx will be equal to h du. Now what we will do, we have to change the limit from x0 to xn to 0 to n. So when we will change it, it will come Pn, that is the forward difference polynomial, x0 plus UH into h into du. Now we will take h at its constant outside 0 to n, and we will put the forward difference formula here, that is y0 plus u delta y0 plus u into u minus 1 by factorial delta square y0 plus u into u minus 1 into u minus 2 by 3 factorial delta cube of y0, like this. So here we have put it this. Now this is the general quadrature form. This is the general quadrature form. Now in this general quadrature formula, if you put n is equal to 1, you will get trapezoidal, the formula for trapezoidal. If you put n is equal to 2, you will get the formula of Simpson's 1 by 3. If you put the value n is equal to 3, you will get Simpson's 3 by 8. If you put value n is equal to 6, you will get Wedel's. So we have concluded our fourth question, where we needed to derive Simpson's 3 by 8, Wedel's, Simpson's 1 by 3, and trapezoidal using general quadrature formula. So we have did this. Now coming on to the fifth question, that is we need to solve this system of linear equations using Gauss elimination with partial pivoting, Jacobi, and Gauss-Seidel method. So first we will be solving this using Gauss elimination with partial pivoting. So first what we will do, we will pivot the first column. So pivoting the first column, what does pivoting mean? Pivoting means placing the largest element at a diagonal position. So here the largest element we could see for in column 1 is 3. So what we need to do, we need to place this 3 in the diagonal position. That is, we need to place it in the row 1 column 1. In the row 1 column 1. So what we would do, we could swap. The best way is to swap these columns. So what we will do, we will swap these columns. Did swapping the columns change anything? No. The swapping the column does not change anything. So we will swap the column and the row 1 is pivoted here. Now what we will do is we will simply apply Gauss elimination. This is the current state of our equation. What we will do now, we need to eliminate this both, and we need to make it 0, because as you know, for Gauss elimination we need to convert the matrix in an upper triangular matrix. So for converting the matrix in upper triangular matrix, we will eliminate this x and this y. So first of all, we will eliminate these two x's. We would first eliminate these x's. So uh, what we'll do in R2, we will put R2 minus 1 by 3 R. What is this 1 by 3? That is this upon coefficient of this upon coefficient of this in minus R1. So after doing this, and first we will apply in R2 and we will apply in R3. What we will do in R3? We will do R3 minus 2 by 3. 2 by 3 2 by 3 R1. है ना? So when we will do this, the equation will are all three equations will this, and you can see the part of x is eliminated. Now what we need to do, we need to eliminate this y part. So first eliminating this y part, we will apply pivoting in column 2. So for applying pivoting in column 2, what we will do, here you can easily see that this is greater than this. So we will swap R2 and R3. Swap R2 and R3. And again for R3, the multiplier is, what will be the multiplier for R3? That is 1.68 upon 1.33, that is 0.5. 0.8, sorry, 0.8. So what we will do, R3 will be R3 minus 0.8 into R2. The x, y, and z terms will be coming, and also the RHS term will be coming, and the upper triangular matrix has been formed here. The upper triangular matrix we have formed here. We have formed the upper triangle matrix. Now what we will do? Now we will perform back substitution. So you can easily see that 1.60 is equal to 4.8, so z will come 3. Now put the value of z here and find the value of y. Now put the value of y and z here and find the value of z. So we will be doing back substitution, and we can easily say that the value of x, y, and z is coming 1, 2, and 3 respectively. So this here we have solved the first question using Gauss elimination, the system of linear equation using Gauss elimination. Now we will solve the same question using Jacobi. So for iterative methods to converge, the matrix must be diagonally dominant. So first of all, before applying Jacobi or Gauss seidel, first we will need to check that the first element is greater than the sum of two or not. So here three is greater than equal to two plus one, that is three. Yes. Here this three is greater than this. No. Yeah, but it is somewhere equals to. So yes, it will work. And here you can say that this three is greater than again two plus one. So yes. So yes, here we can say that Jacobi and Gauss seidel is applicable. Now we can find the value of x in both the equations. So the value of x will come out to be like here what will be 10 minus 2y minus z upon 3, 14 minus 2x minus 2z by 3, and here it will be 14 minus 3z minus 2y upon 14 minus 3z upon 2y. So we will find the value of x, y, and z from these three equations. After finding the value of x, y, z from these three equations, what we will do? We will initialize the firstly x0, y0, and z0 to 0, 0, 0. Now for the first iteration, find the put these values as this is y0, x0, x0, z0, z0, y0. Put these values and find the value of x1, y1, y. So here we have find it the x1, y1, z1. Now what we'll do, put these x1, y1, z1 again here. Now this will act as x1, y1, z1, x1, y1, z1. Now put these x1, y1, z1 here. So you will find x2, y2, z2. Now put these x2, y2, z2 again here. So you will find x3, y3, z3. Okay. So till when we will continue this? We will continue this until our iterations become nearly equal. So Jacobi converges very slowly, but continuing this iteration eventually leads to the exact analytical root. So we will take it to the further iteration, and you could see that till 18th or 19th iteration, the values will come x is equal to 1, y is equal to 2, and z is equal to 3 will come fine. So this is the Jacobi method. Now what we will do, we would be solving this again the linear equations using Gauss seidel method. Now what we will do in Gauss seidel, the same thing we will do. Just in Gauss seidel, what is the thing that y1 will be utilized x1 and z1 will utilize both x1 and y1. For the first iteration, first again x, y, z we will take as 0. We will take as 0. We will find x1. Now, if you have x1, you can use it here. You can use in y1. And when you are coming to z1, you have both x1 and y1. So you can use it. So you can use it. So you can use both in z1. So this is the Gauss seidel. Similarly, in Gauss seidel also you will get the same answer. Now coming to the last part, that is ordinary differential equation. So for ordinary differential equation, we have been given an ordinary differential equation that is dy by dx is equal to x plus y. Initial condition y0 is equal to 1, meaning x0 is equal to 0 and y0 is equal to 1. Means x is 0 and y is 1. So x0 and y0 is given, dy by dx is given. We need to find the value at x is equal to 1. X is equal to 0.1. Step size is h is equal to 0.1. Now the function is this. The function is x plus y. What we need to do? What we need to do? The integrating factor. The integrating factor if is equal to e raised to integration of minus 1 dx, that is e raised to minus x. The exact solution is this, and y of 0.1 is this. What we will do, the formula for Euler method. Formula for Euler method is what? The formula for Euler method is yn plus 1 is equal to yn plus h into f of. So yes, what we will do, the formula for Euler method is this. What we will do now, we will evaluate for step 1, that is x1 is equal to 0.1. So y1 will be equal to y0 plus h into f of x0 comma y0. Y1 will equal, so what will be y1? We will substitute the value. Y0 is 1, h is 0.1, f of x0 plus y0 will be equal to x0 plus y0. Now we will substitute the value and we will find y1 is equal to 1.1. Next, So here y1 is 1.1 at x is equal to 0.1. The Euler method y1 is equal to 1. Now similarly, what we need to do, we need to find the same. We need to find the same y1 using Runge-Kutta fourth order. So using Runge-Kutta fourth order, the h is equal to this, x0 is given, y0 is given. What we need to do? The k1 is, what is the formula for k1? That is h into f of x0 comma y0. That is h is 0.1, and x0 plus y0 is equal to x0 plus y0, that is 0 plus 1. So k1 is equal to 0.1. Similarly, we find K2. K2, the formula for K2 is h into f of x0 plus h by 2, comma y0 plus k1 by 2. So it will be equal to x0 plus h by 2 plus y0 plus k by 2. We will add everything up. Or first, what we can do, h is 0.1, x0 is 0, h by 2 is what? H by 2 is 0.1 by 2, that is 0.005. What is y0? Y0 was 1. Y0 was 1. What is k1? K1 is 0.1. Just we have find it by 2, that is 0.02. Now what we will do? It will be 0.05 plus 1.05, and f of this will be equal to 0.05 plus 1.05 into 0.1. So it will come around 0.1. K2 is this. Similarly, we will find K3 and we will find K4. And as you know, y is equal to what? Y0 plus K1 plus 2K2 plus 2K3 plus K4 by 6. So we will find y1, and we needed to find y1 only. So here the answer is 1.11, or from Euler also the answer was coming 1.11. So Rangikutta is more proficient and it is more good. Now similarly, we need to find again the value of y1 using Pickard's method. So for Pickard's method, the formula is y and x is equal to y0 plus integration of x0 comma x. So for first iteration, y1x is equal to 1 plus integration of 0 to x t plus y0 dt, that will be equal to 1 plus integration 0 to x t plus 1 into dt. So y1 of x is equal to this, and we will integrate it, so it will come somewhere around this. Now for second iteration, we will do the same thing, so this will come. For third iteration, what we will do now, we will need to evaluate y2 at x. Put x is equal to 0.1. Put x is equal to 0.1 in y2, and you will get this. So for the Pickard iteration, continue up and higher order terms with Taylor expansion of this. This is the Pickard method. Now we need to solve the same question using Taylor's method. Taylor's method formula you already know, that yx is equal to y0 plus x into y dash of 0 plus x square by 2 factor y double dash of 0 plus x cube by 3 factor y triple dash of 0. So what we need to do is, what is y0 is already given. What is y dash? Y dash will be x plus y. So what will be y dash of 0? Y dash of 0 will be 1. What is y double dash? That is 1 plus y dash. Y dash is what? Y dash is 1. 1 plus 1. So what is y dash of 0? That will be 1 plus 1 is equal to 2. What is y cube? Y triple dash? That is also 2. What is y 4 dash? That is also 2. So what we will do? Now we will substitute these values in this equation, and we will find the series. Now in this series, you can find the value of y at any point. So now we need to find a value at x is equal to 0.1. So put the value x is equal to 0.1, and you will get the y is equal to 1.00. This perfectly matches the RK4 and analytical evaluation up to 6 seconds. So you can see the Taylor series answers matches exactly with the Runge-Kutta, but not with Euler method. Why? Because Euler method is not correct. We need to apply here Euler predictor corrector also to find the correct answer. So this was the seventh question, and now we come to the end of the solutions of lab assignment 3. So thank you.